Welcome, everyone. Today we have with us Sir Timothy Gowers, who is a research mathematician. And some of his achievements include a perfect score at the IMO and a Fields Medal for his body of work connecting functional analysis and combinatorics. And the list can go on and on. But currently, he's the Royal Society Research Professor at the University of Cambridge and the Roose Ball Chair and Fellow at Trinity College, Cambridge. And in October, he'll be chair de combinatoire at the Collège de France. Today, he'll be talking about if a graph has a few triangles, how do we get rid of them? And on that note, I would like to hand over to Tim. Thank you.
Thank you very much. Perhaps I'll start on a trivial note, which is to say that I feel a slight fraud when people talk about my perfect score at the IMO, because in my year, it was a rather unusually easy one because a lot of countries were participating for the first time, so they didn't want to make it too hard. So there were something like 30 or 40 people who got perfect scores, so it wasn't as special as it would be in another year. Anyway, that's a small point. I'm still very pleased, of course. So what I want to talk about, let me just get my... I should say, by the way, I'm using some technology for the first time ever. So if I make little mistakes, technological mistakes, please bear with me, but I think it's going okay. So what I want to talk about is, I've chosen this, it wasn't very easy to decide what to talk about, but I thought it would be good to talk about something mathematical rather than sort of about more general questions about life as a mathematician and that sort of thing. And I also thought that it would be good to talk a little bit about mathematics at a research level. And I also thought this topic stood out because it's mathematics at a research level, but the problem itself that I want to talk about sort of sounds as though it could be an IMO problem. You don't know until you start thinking about it how difficult it is. So it's a question that looks reasonably innocent, but turns out to be extremely interesting. So now, let me try to say what it is. So first of all, I assume that most people here, if not everybody, know what a graph is, but just in case, I'm going to tell you. So a graph is an object that has, let's try and change the color here. Has some objects that we call vertices, which you can think of as just points. I accidentally hit the wrong button there, right. Right, here are a few points. And we join those points with sort of lines, and those lines are called edges. So if you haven't seen graphs, well, you have, because for example, if you've ever drawn a convex body like a tetrahedron or something like that, then the vertices and the edges form a graph. This particular graph here, by the way, is called K4. It's a complete graph on 4 vertices. That means we have 4 vertices and every single possible edge that you could put in is in, so it's complete. So there are a couple of graphs. A triangle in a graph is exactly what you think it is. It's just 3 vertices that are all, oops, don't know how that happened. That are all, I don't know what I'm doing here. I'll do it down here. Maybe I went over the margin or something. That's better. No, it's... Okay. That is a mystery to me. Never mind. A triangle is 3 vertices that are all joined to each other. And so we say that a graph is triangle free if it doesn't contain any triangles. And there are lots of interesting questions about triangle-free graphs. Unfortunately, I haven't got time for those right now. What I'm talking about is graphs that haven't got very many triangles. Now, what does that mean? Let's get a sort of little idea of what it means to say that a graph hasn't got very many triangles. So let's take a graph which I'll call G, and let's suppose that G has n vertices. So I'm going to start with an extremely simple question. How many triangles could G possibly have? Well, each triangle has 3 vertices. The number of ways of choosing 3 vertices is n choose 3. So there cannot possibly be more than n choose 3 triangles. And if we take the complete graph with n vertices, then obviously it has got n choose 3 triangles. And just, we know that n choose 3 is n minus 1, n minus 2 over 6. And that's pretty close to n cubed over 6 when n is large, because we don't care about the difference between n minus 1 and n and that sort of thing. So we've got roughly n cubed over 6 as a maximum number of triangles. So when I say that G has few triangles, I mean, I'm going to use university notation. I use the letter delta, the Greek letter delta, just to stand for a very small number like 10 to the minus 10 or something, a very small positive real number. So a few triangles means at most delta n cubed, where delta I do not understand this at all.
You might be accidentally pressing a button on your pen because that undoes the last move.
Yeah, but I don't think I am.
Oh.
Okay, let's go back to I think I'll just move to another page. So just remember that few triangles means a very small fraction of the maximum possible number of triangles. And just while we're at it, let's also talk about what it would mean to have few edges, or what would. So again, the maximum number of edges is n choose 2. There we are, that's the maximum number of edges, which is roughly n squared over 2. So we'll say that few edges means at most epsilon n squared. I mean, epsilon is another small positive real number. So the question is very simple. And I think it's going to be easy to type it. So if G has few triangles, here's the big question. Now, how do I want to make that precise? To make that precise, what I would say is, supposing you give me an epsilon, like 1 over 100. So you give me some small number. Is there a delta, a positive delta, with the property that if for any graph with at most delta n cubed triangles, I can remove at most epsilon n squared edges to make it triangle free. So I don't mind, so the smallness of the number of triangles could be much smaller than the smallness of the number of edges. I'll allow that. But all I want to know is just, if you give me some notion of smallness, this epsilon measures the number of edges that we're allowed to remove. So in a sense, it's saying that if you remove just epsilon n squared edges from a graph, you attain a new graph that's approximately the same as the original graph. It just differs by at most epsilon n squared edges, which is a small number of edges. So if you tell me how well I need to approximate my graph with few triangles by a graph with no triangles, can I give you some delta so that if a graph has at most delta n cubed triangles, then it can be approximated by a graph that's triangle free and approximated to within epsilon. And let me just, well, perhaps it's a bit silly not to tell you straight away what the answer to this is. It's yes. And this is a theorem of Imre Ruja and Endre Szemerédi, two extremely famous combinatorialists and from Hungary, two of my favorite mathematicians, as it happens. But before I go into why that's the case, I want to talk about something else and talk about a sort of equivalent version of this result.
So Tim, there's a question in the chat, which is,
Sure.
What's the purpose of approximating n choose 3 to n cube? And why not directly say delta n choose 3?
There's no reason. You could just as happily say delta n choose 3. It's just that when you're writing a paper, it's more convenient to write n cubed than it is to write n choose 3. It's because the difference between n cubed and n choose 3 is a factor of 3, but the level of precision that we can expect in the results, as we'll see in a moment, is such that a factor of 3 really makes no difference at all. So it's not an important choice to say delta n cubed, it's just a choice made for convenience. But that's a good question. Okay, so I'm going to define for you something called a hypergraph. So a graph, you have points. That time I did touch a button by mistake on the pen. You have points, and you join them by edges. And we'll just have to, for a hypergraph, I don't understand it. It was working really quite well before.
I think they'll just appear eventually. It takes some time to load up. Yeah.
Oh, maybe that's what it is. It's just a delay. Okay, I'll stop worrying about it and see what happens. So for a hypergraph, we take triples of points. Well, actually, what I'm talking about is a 3 uniform hypergraph. So whereas we can represent an edge of a graph by just a single line, a hypergraph, a 3 uniform hypergraph edge, we can represent by a triangle, which, there we go, it's filled in for me. So this is going to be slightly challenging with this delay, but I hope it'll work. So we might have some more points. Joined up by some more triangles. So this really is quite a prodigious delay. But anyway, what I've shown you is an example of a hypergraph with 3 hyperedges. And how many vertices? 6 vertices. 1, 2, 3, or 3 inner ones and 3 outer ones. And the 3 hyperedges are this triangle here, and this triangle here. Now, actually, that's quite an important hypergraph for this story, because let's consider the following situation. So take in a graph a maximal edge disjoint set of triangles. So what does that mean? That means I just take a triangle, I take another one that doesn't share an edge with the first triangle, and a third one that doesn't share an edge with the first 2 triangles, and I keep going and I keep going. So because they're edge disjoint, I can't have more than the number of edges in the graph divided by 3. So, but let's say the following: if there are at least epsilon times n squared triangles in the set, then we can't remove epsilon n squared edges and get rid of all triangles, because you have to remove an edge from each of those edge disjoint triangles if you want to get rid of all those triangles. But actually the converse is true. So supposing the maximal edge disjoint set of triangles, supposing there are m triangles, and I just remove all those triangles, then there'll be no triangles left, because if there was a triangle left, it would have to share an edge with one of the original triangles that I've just removed, and those formed a maximal set of edge disjoint triangles, because that was a maximal disjoint set. So I must have removed at least one edge from every triangle. So the converse holds up to a factor of 3, because I've removed 3 times the number of edges as there were triangles in the disjoint set. Now, using that observation, I think I won't give the argument in full, but using that observation, one can prove that the triangle removal lemma is equivalent to the following statement. Suppose I take a 3 uniform hypergraph, and it has the property that none of its hyperedges share an edge. So what I've drawn here is actually a 3 uniform hypergraph, because this triangle doesn't share an edge with this triangle, and this triangle doesn't share an edge with this triangle. So none of the 3 triangles share an edge. They're allowed to share a vertex, but not an edge. Then the statement is, if I have a 3 uniform hypergraph that's, we call them linear, for a reason I won't go into, but if we have a linear 3 uniform hypergraph, i.e. one where no 2 hyperedges, no 2 triangles in the hypergraph share an edge, then it must actually contain, and if it's got at least epsilon n squared hyperedges, then it must contain at least delta n cubed of these things here. You can see the relationship between these things here and triangles, because not only are these triangles, if we form a graph out of all the edges that we used to make these triangles, then that graph contains not just these triangles, but also this triangle here. So each time you contain one of these objects, which in one paper was called a triforce, because apparently, I haven't seen Star Wars, but apparently it looks like something to do with Star Wars. So if you contain if the graph that you make out of the hypergraph by taking the triangles and just drawing the edges contains a triforce, then that triforce is responsible not just for the 3 outer triangles, but also for an inner triangle that was not part of the hypergraph. So if you can show that you've got lots of triforces, then the underlying graph contains lots of triangles. So again, I didn't really give the full details there, but I'm hoping that you'll believe me that this triangle removal lemma is equivalent to a statement that says if you've got enough triangles in a linear hypergraph, then it forces you to have lots of triforces. Right, so let's move on. I want to give you just a very brief idea of how the triangle removal lemma is proved. And it uses an amazing result called Szemerédi's regularity lemma. Szemerédi's regularity lemma says, perhaps I'll just, I will type that because it's so important. It says, if you've got a graph, then you can partition its vertex set into a small number of pieces. By the way, we've also fixed some small epsilon. So the number of pieces that I'm going to partition into will depend on epsilon. And we'll come to how it depends on epsilon in a moment. Well, of course, we can partition the vertices of any graph however we like, but this partition has a very special property, which is that for almost all pairs, if you look at just the portion of the graph, or just the edges of the graph that join, this is playing up again, but let's just concentrate here. Just look at the edges that join the two vertex sets between those two parts. Almost all of those look like random graphs. Now, exactly what it means to say looks random would take a little bit of time to make precise. I hope that will reappear at some point.
There might be some background applications or something. Okay, it appeared.
So what you should imagine, and since drawing is a challenge, I'll just say it. What you should imagine is that all these pairs of blobs are joined with things like that. And all of these, except maybe just a few exceptions, behave very much like random graphs of the same density. So just imagine that the edges were scattered randomly, and of the possible edges, you had so I don't know what I was about to say there. So let's now, so you could actually make them exactly random. You could just pick a probability like 1/3, and you could say, I'll choose each edge independently with probability 1/3. And that would give you a very good example of a graph that looks random, because it has in fact been chosen randomly. And unless you're very unlucky, it will have lots of particular sorts of properties that we like. Now, what the regularity, so what can we, what do we do once we've got the regularity lemma? We do the following. This is a trick that is a very standard thing to do in lots of applications of the regularity lemma. Throw away sparse pairs and non-random pairs. So remember, we're going to be assuming that our graph hasn't got very many triangles. We're trying to throw away a small number of edges and get rid of all triangles. And this is what we have to do, it turns out. So what is a sparse pair? A sparse pair is a pair that just hasn't got very many edges. So if we throw away all the edges from sparse pairs, then we're not throwing away very many edges. Because by definition, a sparse pair didn't have very many edges. The non-random pairs, well, the regularity lemma tells us that there aren't very many non-random pairs. So if we throw away the non-random pairs, then by the regularity lemma, we're not throwing away very many edges. Just imagine that all these blobs have roughly the same size, just for convenience. So once we've done that, we're left with the graph that's like this, but we have the additional information that whenever you've got an edge between two blobs like this, this graph here doesn't just look random, but it's also reasonably dense, because we got rid of all the ones that weren't random and all the ones that weren't dense. Now I claim that that graph does not contain a triangle. We've thrown away not very many edges. I claim that there's no triangle. So for that, I think it's useful to have another picture. So let's hope it works. So if there is a triangle, then it's going to have to, its edges are going to have to connect three of these blobs. By the way, we could also throw away the edges inside the blobs. And if there are enough blobs, then that's also not going to be very many edges. So I can assume that the triangle connects different blobs like that. Now, if we've got a triangle like that, that tells me that there's an edge here. So it means I didn't throw away this particular, all the edges between this one and this one. So therefore, the graph that joins this must be dense and random looking. So I've got a sort of random jumble of edges here, and I've got a random jumble of edges here, and lots of them, and a random jumble of edges here, and lots of them. But if you've got three random graphs joining three reasonably large sets, then because of their random-like behavior, they form lots of triangles. To avoid triangles, you'd have to behave in a very special way, and random graphs don't behave in that special way. Again, that's obviously an argument that needs to be made precise, but it can be made precise. So we get from the fact that there was one triangle that there had to be lots of triangles. But the assumption was that there weren't lots of triangles, and therefore there couldn't be any triangles in the graph once I'd removed the sparse and non-random pairs. So I'll say that once again. First, you remove the sparse pairs and the non-random pairs. Then whenever you've got a triangle, that means, let's just say hypothetically, if there were a triangle, you would have to have three dense random-like pairs, and that would give you lots of triangles. So if you start with the assumption that there aren't lots of triangles, then you get that once you've removed the sparse and non-random pairs, you've got rid of all triangles. But when I said there were lots of triangles here, actually, how many did I mean? Well, let's just think about that a little bit. So I said, let's assume that these blobs were about the same size. So the whole thing depends on how many blobs there are. So if this blob has size, let's call it M. And just let's assume they've got exactly the same size, just for simplicity. So if they've all got size M, and these are all reasonably dense. Let's say that they've all got density at least some number like alpha. See if I have any better luck with an alpha down here. No. Then that'll tell us that the number of triangles is going to be roughly alpha cubed times m cubed. That's what we'd get in a random graph, because each triangle has a probability alpha cubed of belonging to the, at least alpha cubed of belonging to the graph. So if I have alpha cubed, m cubed triangles, alpha is a reasonably large constant, but m, how big is m? Well, m is roughly n divided by the number of blobs that I took. So it all goes back to the question that I mentioned earlier: how does the number of blobs that we have depend on the epsilon, which was the degree to which the graph is approximately random-like. And the dependence turns out to be really extremely bad. I will maybe devote a new slide to this. How big does m have to be? Well, we can do it as long as, sorry, how big does a number of blobs have to be? That's not m, that's k. That's less than or equal to 2 to the 2 to the 2 to the 2. And the proof given in the regularity lemma, oh, it's come out. So that's meant to be a tower of height 2s. There's a tower of 2s of height 1 over epsilon to the 5. So if epsilon is 1 over 100, that number is going to be well over 1,000,000, and we take a tower of 2s of height 1,000,000. So this is a very, very bad dependence. So you might think, well, that's just a lazy proof if you get a bound as bad as that. But actually, a result of mine from quite some time ago now showed that actually something like this, not necessarily 1 over epsilon to the 5, but at least 1 over some power epsilon. I got 1 over epsilon to the 1 over 16, and I think now it's known that it's 1 over epsilon will do. So I actually found a graph where you really do need that number of blobs for the regularity lemma to work. So we get this ridiculous dependence, and it turns out so what that translates into for the triangle removal lemma is, maybe I'll do this again in a different slide. If you want to know how delta needs to be, well, I'll give you what's known, which is a bit better than comes out of the regularity lemma. So you're all right as long as delta is less than or equal to 1 over two to the 2 to the 2 to the 2, but this time the height is only log 1 over epsilon. And this bound here, so what I'm saying here is, supposing you want to remove at most epsilon n squared edges from your graph to get rid of all triangles, you'll be okay if there are at most delta n cubed triangles, as long as delta is smaller than this number here. And that was due to another very good combinatorialist called Jacob Fox. Now, I'm going to stop in a moment because I've had half an hour, and that was roughly how long I intended to take. I was going to give you, but I think I don't really have time to do this, but I'm going to give you a consequence of this result, just to give an indication of why we care about it. So, by the way, I also want to point out that we do not know of graphs for which anything like this smaller delta is necessary. So I better write that down, actually. So for all we know, delta less than 1 over e to the log 1 over epsilon squared is enough. So let me just go back to what we can prove it for. We can prove it for that, but it might be that that's enough. So I could have just equally written delta less than or equal to, and this isn't. So you see there's a massive, massive, massive gap between what we know and what we can prove. So what we can prove and what might be the case. So very briefly, why do we care about this? It's because it gives us another proof of a known result called Roth's theorem. It says, for all delta greater than 0, there exists an n such that if A is a subset of 1 to n, and the size of A is at least delta n, then A contains an arithmetic progression of length 3. This has been in the news recently, actually, because we also care about how large n needs to be in terms of delta. And very recently, that bound was improved in an important way. But the point is that the triangle removal lemma gives a proof of Roth's theorem, but because the bound in the triangle removal lemma is rather bad, the bound it gives for Roth's theorem is rather bad. And we're extremely interesting to, and the triangle removal lemma has a number of other consequences. all of which would be greatly improved if we had better bounds for the triangle removal lemma. So it's not just a very beautiful theorem in combinatorics, but it also is an extremely interesting open problem, or at least the open problem is how large does delta, so how small does delta really need to be for the triangle removal lemma to be valid? So I'll stop there and take questions. So the plan is that I'm very happy to take questions on the mathematical content of this talk. Maybe we could try and do that more first, but then I'm also very happy to move into more general type questions as well. So that's it for the mathematics.
Could you elaborate more on what it means for a graph to look random?
Yes, okay, that's a good idea. So it turns out that there is a whole theory of objects called quasi-random graphs. And so the answer to your question is that I could give several different answers. And I will give two different answers. And the point about this is that they are equivalent. So if a graph has one property, then it automatically has the other property, maybe with slightly different parameters. So one property is, here's my, whoops. I've got a graph, which I'll just represent as a blob, a single blob. So you should imagine that filled with vertices and edges. Now let's just take two sub-blobs of that blob. Oh, by the way, the graph has density p, so that means it's got p times n choose 2 edges. So what I want to say is that this graph looks like a graph where I just chose each edge with probability p independently. So if I had such a graph, how many edges would I expect between a set A here and a set B here, which I can't seem to write? The number of edges I would expect is P times the size of A times the size of B. See if I can write that more easily than I can draw it. The number of edges I would expect is P times the size of A times the size of B. That's because I'm assuming that A and B are disjoint here. So the number of pairs, one vertex in A and one vertex in B, is exactly the size of A times the size of B. And if each one is in with probability P, I'll get P times the size of A times the size of B. So a property that you would expect of a random graph is that for every pair of sets A and B, you get roughly P times the size of A times the size of B edges. A quasi-random graph is one for which that condition holds, i.e. for at least every reasonably large pair of sets A and B, you get approximately P times the size of A times the size of B edges joining them. Another property you would expect is that given any small graph, like a triangle, you'd get the roughly the expected number of copies of that small graph. So how many triangles would you expect in a random graph with edge probability P? You would expect P times n choose 3. Because there are n choose 3 possible triangles, each one, sorry, P cubed times n choose 3. Because there are, because each triangle has a probability of P cubed of belonging to the graph. Now, having P, that result for triangles doesn't guarantee, so if you've got roughly P cubed n choose 3 triangles, that doesn't force the graph to look random-like. But it turns out that if you've got roughly P to the 4th, n to the 4th 4 cycles, so a 4 cycle looks like this. So if you've got roughly P to the 4, n choose 4, do I mean n choose 4? Anyway, P to the 4th times the maximum number of these that you could possibly have. It's not going to be n choose 4 because there's not a sort of symmetry between all the 4 vertices, but never mind. Then the graph is forced to look random. So that's another completely different condition, which actually also then turns out to imply that the graph contains roughly the right number of copies of every small subgraph. But there are several other properties as well. So basically, there are a number of different properties that you get with high probability when you pick a graph at random. And it turns out that a lot of those are approximately equivalent to each other. And they give this very useful notion of a quasi-random graph. For the Szemerédi's regularity lemma, we have to talk about quasi-random bipartite graphs. So that's graphs where all the edges go from one vertex set to another vertex set. Such graphs are not quasi-random in this sense, but they're sort of they can be quasi-random given that they are bipartite, so to speak.
Thank you. Yeah, that makes sense. So if there are any more questions related to the topics of this talk, we can have them now. Else I could proceed for the more general questions. Yeah, I think not. So we could proceed to the more general questions then. And
I'm going to stop sharing my screen, but I can obviously reshare it if.
Yeah, that's all right.
There we are.
So, yes, Fields medal questions. Let's address those first. Wait, sorry, there's a question first which says, how would it behave for cycles of their lengths? Could the question be clarified? How would it behave for cycles of other lengths? Randomness.
Yeah, if the cycle has odd length, it doesn't help at all to make it quite random. So for example, every bipartite graph fails to contain any odd cycles, and a bipartite graph as a graph, not as a bipartite graph, as a bipartite graph is very far from being quasi-random because you've got a huge, great sort of empty part to it. But it turns out that every even cycle works. So for fixed size. So if I don't contain cycles of length 18, then if I contain roughly the expected number of cycles of length 18 for a graph of that density, then that forces the graph to be quasi-random. In other words, to look random in lots of different ways.
Just as an extension, so could you readily think of any? Okay, Freddie is asking, shouldn't it be the opposite? Sorry.
Because like bipartite graphs like also have a expected number of even cycles, but not of odd cycles. So like a bipartite graph wouldn't have the expected number of odd cycles, therefore it wouldn't be.
Yeah, that's what I was saying. So, so if you know that a graph doesn't contain an expected number of odd cycles, sorry, if you know that a graph, oh, wait a minute. Yes, no, that wasn't a perfect example at all. What do I want to say? I want to have a graph that contains roughly the right number of triangles. Yeah, so it's not, I think maybe it's not so easy to do in my head, I beg your pardon. So I think, but using the fact that bipartite graphs contain no triangles and then maybe some sort of intermediate value theorem type thing, you could take a bipartite graph here and a complete graph here that contains far too many triangles and sort of adjust their sizes until you get exactly the right number of triangles for the given density. So if it's all complete, you've got, no, that doesn't work. Okay, if I take a complete tripartite graph, so all the edges, I think that'll have too many triangles for the density. And if I take a bipartite graph, that'll have too few. And if I now sort of slowly shrink the tripartite graph and increase the bipartite graph, there'll be some sweet spot in between where I've got exactly the right number, but the graph will look very far from random. I think something like that would work. Maybe something simpler could do it. But you're absolutely right to pick me up on that.
Okay. Yeah, that's great intuition. So, yeah, the question is, did you ever consciously think about winning a Fields Medal in your career at any stage? And what's your advice for anyone wanting to get to that stage in life?
Yeah, so I think my answer to that would be, don't go into mathematics because you want to get a Fields Medal. That would be ridiculous. You have to love the subject. Even if you do extremely good research, there's still a sort of luck element to it, and you know, maybe the committee just happens to prefer somebody else's research. Is not objectively better than yours or something, but and I think if you become so sort of speaking for myself, obviously, you know, every young mathematician sort of dreams of it in a way, you know, sort of think it would be an amazing thing to do. But it's a bit like sort of when you're a child, you dream of being an astronaut and going to the moon or something. Sort of, it would be incredible to do it, but not very many people do it. And, but as with many things in life, if you aim directly for that, that's a mistake. You have to aim directly. What you should be aiming for is to obtain the most interesting mathematical results you possibly can, without worrying about what the consequences will be from, as far as sort of recognition from other people is concerned. And if you're lucky, well, you know, sort of lucky few, it works out. But I think sort of, I mean, maybe there are sort of genuine decisions one might have to make. So supposing, for example, you thought such and such an area tends to get more Fields medals than such and such another area of mathematics, so I'm going to go into the first area. I think that's the sort of decision that you could make that would be a big mistake. If you want to maximize your chances, which again, I'm not saying is the sort of should be uppermost in your mind, but if you want to maximize your chances, the best thing to do is to do the area that you like the best, because that's where you're going to do the best work. And I'm partly speaking from my own experience. I worked in an area that was regarded as very unfashionable, the geometry of Banach spaces. And because that's what I liked, and I then had the good fortune that it sort of worked out. But I mean, another point about that is that areas sort of change in their fashionability. So combinatorics, which I worked in as well, was also extremely unfashionable for a long time, and then now that's changed a lot. So really, the best advice is don't go in for it for that. Do the mathematics you love. Work as hard as you possibly can.
So just in terms of getting recognition and all, how often do mathematicians publish usually, and how hard is it?
That is something that there's no sort of universal answer to. It varies a huge amount by area, and it also varies a huge amount by person. So a lot of people in combinatorics publish lots and lots of papers. Sort of, there are combinatorists, some of the top combinatorists have published sort of approaching 1,000 papers over a career. So if you work that out, you know, if they've worked for 50 years, then they're talking 20 papers a year or something. That's a little bit crazy, I think. And I've always preferred myself, but I'm not saying that it's the approach that everyone should follow, but I've preferred publishing fewer papers and making them sort of longer and more substantial. Right. Of course, if I discover something that can be written in a short paper that's maybe not too earth-shattering, that doesn't mean I will refuse to publish it or anything like that, but just sort of I don't like sort of trying to get lots of papers.
Right.
But that's just combinatorics, and there are other areas where it really would be impossible to produce the number of papers that are produced by some people in combinatorics. So if you do algebraic number theory or parts of geometry and things like that, I think there again, the tendency is more to publish fewer papers that take longer to produce. So that actually, that's one reason that measuring people by, there's a lot of measuring that goes on in academia by sort of counting people's papers and citations and things like that. And it's absolutely ridiculous because it all varies a lot by what area of maths you're doing. And no one's going to say that people in one area are on average better than people in another area because they're all getting more citations and more papers. Yeah. But actually, maybe the more interesting question is how hard is it? So when you start with research, you can often think, well, there are lots and lots of very clever people who've thought about these problems with years of experience behind them of doing research. What chance have I, as a beginner, got of solving this problem or discovering something new? And there, I think there are answers to that question. So one answer is, if you try a question that really has been tried by lots and lots and lots of people, then your chances of success are very small, at least to start with. But there are plenty of problems around. Each problem people solve tends to spawn a whole lot of new questions. And so because of that, there are lots of questions around that have not received all that much attention, some of which are very interesting. And also, the more you do research, the more you find that when you work on one question, then you have an idea that turns out to be interesting and useful for another question that you happen to know of. So that can happen. And it happens more and more as you get acquainted with more and more mathematics. And that way, you sometimes find, if you're lucky, that you suddenly realize you had an insight that is applicable to some really quite famous problem that people have tried. So I would say that really big problems, it's very, very difficult to solve right away when you start research. But when you gain an experience, you start to sort of become sensitive to the fact that you might have had an insight that would be useful for a big problem. So it's always good to think about big problems, not necessarily in the hope of immediately solving them, but just to get a feel for what their difficulties are, in case one day you suddenly realize that one of those difficulties might no longer be as difficult as people had thought because of some development in mathematics. So it is hard, but it's not impossible. That's the really important message. And it's also a probabilistic process. Sort of, if you want to solve interesting things, you have to be prepared for the fact that 90% of the problems you try, you won't have much success on. But it's those 10% that you're looking for.
Right. Yeah, so the next question is more about, do you have a flow state when you do maths, or what's your routine to get into the state of mind?
Yeah.
You'll be doing some maths now.
I think sometimes I do get into I assume this means a sort of slightly hypnotic state where all other distractions kind of disappear and you're just absorbed completely in the mathematics.
I think it's from some anime. I'm very certain.
Oh, right. Okay. Well, I was just guessing there. So I don't have a particular insight into how to do that. I think just maybe just setting up, avoiding sort of checking your email or social media every 5 minutes is probably useful. Yeah. Maybe just sort of deciding that because it's very tempting when you do research that at the moment you feel a little bit stuck, you do something else. And it might even be thinking about another piece of mathematics. Like in the worst case, it is just surfing the internet or something. But even in a better case, you might say, I'm a little bit stuck on this problem. I'm just going to think about something else. And sometimes that's good. If you're sort of really properly stuck, sometimes it's good just to sort of do something a bit more fun because, and then you come back fresh to the old problem and you find you're not as stuck as you thought you were. That often happens. But you mustn't do that too quickly, particularly if you want to get into this sort of flow state. And I don't know how important it is. I have sometimes had, maybe not, I have occasionally had moments where everything seems to happen much more easily in my research than usual, and that's very exciting. But I think, I'm not sure whether that's just because of some funny meditative state in my brain. I think sometimes it's just that I've done a lot of stuff that doesn't feel like that at all and gone down lots of dead ends and things. And that's prepared the ground so that at some point, everything feels easier because it actually is easier because I did all the difficult stuff at some earlier stage, the sort of difficult, frustrating part. And then I'm trying to think of a good analogy. I suppose it's maybe a little bit like doing a jigsaw puzzle where you start and it's incredibly difficult. You take ages finding pieces and so on. And then just towards the end, suddenly it seems to be much easier to find a piece to put into a given place. And that's because it is easy. There aren't so many pieces around. I think it's a little bit like that with research. You're not sort of, when you're doing a jigsaw and getting towards the end, it's not because you've suddenly become a jigsaw ninja who's sort of spectacularly talented.
Right. So the next question is, what do you think about Euclidean geometry? Because from a physics point of view, it's not really relevant to our universe. And most of the work, it feels like, has been done already. And there's not a lot of current research in the field of Euclidean geometry. So do we study it just to develop a problem-solving skill at this level?
It rather depends what you count as Euclidean geometry. So if you're talking about sort of IMO problems to do with triangles or something like that, then not many people are doing that kind of thing at the research level. There are interesting questions you can ask, like trying to study the problem very much in the abstract and sort of looking at the set of all points that you can construct within k steps using a ruler and compass and examining its properties and that sort of thing. That gives you some insight into the problems. But Euclidean geometry, in the sense of just, you have the Euclidean plane, which has a certain notion of distance. You need to study it in the sense of, you need to know about Euclidean geometry, not so much what Euclid did, but when so there are various different forms of geometry, like Riemannian geometry, spherical geometry, hyperbolic geometry, and Euclidean geometry is one of them. It's the one that happens to be flat in a certain sense. And that's very important background knowledge for any working mathematician. There are also there's a very interesting area of combinatorics called combinatorial geometry, which contains some interesting problems in the Euclidean plane, such as, so the following is an very famous unsolved problem of Erdős. If you have n points in the plane, how many pairs of such points can be at distance 1 from each other? So if I arrange all the points in a line, then I obviously get n-1 pairs. The question is, can you beat that by power? Could you get n to the 1.1 or something like that, pairs of numbers? It's believed that you can't, but we don't have a proof of that. So that's a question formulated entirely within Euclidean geometry. It's nothing like the sorts of questions that Euclid was looking at, but it is Euclidean geometry, and it's a research problem that's attracted a lot of attention. There's a related problem, which asks, how many distinct distances must there be? So again, if you arrange the points in a line, then there must be n distinct distances, and you can do a little bit better than n. Can you have significantly fewer than n distinct distances? And if you can't have more than n distances that are equal to each other, then you certainly can't have fewer than n distinct distances by the pigeonhole principle. Turns out that the distinct distances problem, well, that was also unsolved for a very long time, but that has now been solved by a brilliantly clever method by people Larry Guth and Nets Katz. It was a famous result from the last few years. But the unit distance problem is still open.
Okay. So do you have any advice for current IMO contestants who want to become mathematicians?
Maybe two things I would say. They go slightly against each other, but that's the way it is. So one thing is, when you go to university, really do work hard on, so to speak, the boring stuff. So really learn the important basics of university level mathematics, linear algebra, analysis, group theory, probability, combinatorics, and so on. And some of that will be learning proofs of theorems, which is nothing like as interesting as solving IMO problems, because you're sort of just learning proofs that other people have come up with. But it's something you really have to do it opens the door to a vastly more interesting collection of problems. But when I say opens the door, it doesn't just allow you to formulate them, but it also gives you the tools to solve them, or some of the tools you're doing. So, on the other hand, I think you could just say, well, I'll forget about problem solving for now, and I'll concentrate on learning stuff for 3 years or 4 years or however long you have to be at university. But I think that's a mistake as well. If you've done the IMO, you've got a lot of skill in solving problems, and you really want to keep that, because when you do research, that becomes important again. It's maybe not quite as important for it has some importance, but not quite as important for learning undergraduate mathematics. But if you lose sight of it completely, then that'll harm you when you want to do research, because doing research is problem solving. But it is very important also to bear in mind that when you do research, although the sort of problem solving skill that you have as an IMO contestant is important, it's not all there is to it. So when you do an IMO problem, you know that somebody has set that problem, you know it's got a solution, you know that it's not completely unreasonable to expect you to solve it in an hour or two. With a research problem, the problems are set by, I don't know, what your religious beliefs are, but, or not at all. They just sort of bubble up. And when a problem bubbles up, you don't know at all whether it's going to be hard or easy. You learn to develop a feel for it, but you don't actually know in advance. Sometimes they surprise you, they turn out to be disappointingly easy. Sometimes they turn out to be equivalent to problems that have been open for decades. Sometimes they hit the sweet spot where they're difficult but not impossible, and so when you solve them, you've got an interesting result. And the average length of time to solve one of these problems is much, much longer than 2 hours. You know, it can be months or years. So when you've got a problem that takes a very, very long time like that to solve, you have to worry away at it, and you have to be prepared to say, I'm actually going to give up on trying to solve this problem and try something else. So selecting what to work on is a big part of research life, in a way that it's not for the IMO, because you're just told what to work on. And but when I say that the problem solving that you need in IMO is useful, that's because when you have a problem, an open problem, that sort of develops into a big project, and it spawns lots of sub-problems. And some of those sub-problems do sort of have the flavor of an IMO problem, something that you ought to be able to answer in an afternoon and that kind of thing. So if you've got the skill to answer those sorts of smaller problems, then it will speed up the process of solving the big problems. So I suppose that piece of advice would be that IMO type skill is by no means sufficient for solving research problems, but it's definitely extremely useful. So don't lose sight of that, but also don't lose sight of the other components.
So do you think the people who did IMO in their early years have some advantage when they're research mathematicians? And does it influence the kind of areas they work on? Because you work in combinatorics, and did the IMO influence that?
Well, I don't know. It's very interesting to know whether it worked, how much of an influence it has. I mean, there are plenty of IMO contestants who've gone on to great success in areas that are very, very different from combinatorics. So for some reason, I'm thinking of Richard Taylor. So he works in algebraic number theory, an area where you have to learn a lot of stuff before you can start. You have to learn a huge amount of theory to have any chance of making progress in that area. So that's got a very different flavor from an IMO type thing where you solve problems from first principles, and combinatorics, which is not completely first principles, but it's a lot closer to first principles than algebraic number theory. So I feel that it's more my own temperament. I've always liked problems where you can just dive in and start thinking about them. You don't have to do too much reading first. I think of it as a form of laziness in a way, but it's one that's been quite useful for me, but it doesn't suit everybody. But then you could still ask whether within the areas that people solve, are IMO contestants slightly sort of drawn to certain sorts of problems rather than others? I would say maybe there's a weak correlation, but I don't know. I would speculate that there is a weak correlation, but when I say weak correlation, I mean there is a positive correlation, but it's weak.
Okay.
That would be my guess, but I have absolutely no idea whether that guess is correct.
So what's your attitude towards applied mathematics? Did you ever consider doing it in your undergrad years?
In my first year, I happened to do quite well in applied mathematics in the end of year exams, which made me think perhaps, yeah, up to then I'd always thought of myself as a pure mathematician. I thought, well, maybe I should sort of think about it. But then it gradually became clear to me that actually, maybe another thing to say is that I've always slightly regretted that I never properly learnt quantum mechanics and general relativity, because I sort of feel that's something that should be part of the education of any self-respecting scientific person of whom I count myself as one. But unfortunately, I never did that. But in the end, I realized pretty quickly that I am a pure mathematician, not an applied mathematician. I really like the process of finding proofs.
Right.
So I've got the greatest respect for applied mathematics, and it's definitely, you can do different things if your criterion, the way I see the difference between pure maths and applied maths, a lot of people like to say there's no clear boundary, and I think that's true to some extent. But I think there is a sort of fuzzy boundary, and roughly speaking, it's how much you care about proofs. So if you're an applied mathematician, you may well think, well, there are very strong heuristic arguments in favor of this, and it also agrees with computational experiments. So it's obviously true. And if you're wanting to apply that piece of mathematics, then that may well be a strong enough argument. It may be clear to any right-thinking person that something's true, even if we don't know how to prove it. And I think that's perfectly valid. It's just that when I see such a thing, I also think, well, it would be really nice to prove it rigorously. Not because I'm worried that it's not true, but just because finding proofs, the process of finding proofs tends to throw up lots of very, very interesting questions that, and often leads to developments that were unexpected. So we don't prove things just to check whether they're true or not. We also prove them because we find interesting maths that way.
Wonderful. How many hours do you do research every day?
That varies a lot, actually, from day to day, because I go through phases. Some days I've got quite a lot of administration to do, and that's really annoying, but it has to be done. Some days, or some not. When you do research, there's a sort of cycle that you go through. There's the sort of pure research phase where you're just thinking about stuff and trying to solve a problem. Then there's a writing up phase where you've basically solved it, but there are a lot of details to work out. And then maybe there's other stages where you've got a first draft, but you're not very happy with parts of it. And so that's not even working out details. It's just trying to explain a bit better what you've already written. And the thinking about the problems is the fun part, but you have to do the other parts as well, or nobody listens to, nobody gets to hear about what you've done. So if you've got, as sometimes happens to me, if you've got a sort of backlog of papers that really need to get sent off, then sometimes you just have to say, I really hate to say this, but I'm going to have to spend the next month not really thinking about problems very much and concentrating more on finishing these papers that are unfinished. But if I'm in a day where I devote most of the day to research, then perhaps it could be anything from a couple of hours to 6 or 7 hours or something like that. depending on how well things go, really.
And when you're not doing maths, how do you use your spare time? And we know you're a musician, right?
Yeah, I like doing. I like playing piano, playing jazz piano in particular. And I do other things that everybody does. I sort of read quite a lot and have a garden that needs attention from time to time. And yeah, I suppose.
Right.
Those might be the main.
I would like to thank you very much for your time, Tim.
It was a pleasure.
If there, yeah, I don't think there are any more questions. Yeah, thank you very much.
Right.